We are going to consider here the free electron gas approximation, which is the simplest model we consider, and here we're going to calculate the eigenfunctions corresponding to the Hamiltonian associated to this free electron gas approximation. Well, first, it's important to remark that the system is completely specified by its electronic density. The electronic density is the number of electrons over V, which is the volume of the crystal. Or alternatively, we can also use the average distance between the electrons, the average interelectronic distance, which is this RS parameter. And of course, this RS parameter is going to be related with the electronic density. And what's the relation between them? For that, to calculate it, we can consider that each electron occupies like a sphere of radius RS. And we can calculate which is the volume of that sphere corresponding to that each electron is occupying. So the volume is 4 over 3 pi rs to q to 3, which has to be equal to the volume corresponding to each electron, which is the total volume over the number of electrons. So this is actually 1 over n, which is the 1 over the electronic density. So from here we can extract Rs in terms of the density, and that's the expression we have between the average interelectronic density and average interelectronic distance and the electronic density. So as I've said before here, we're interested in calculating the eigenfunctions of this free electron gas approximation. So in order to get we have to solve that equation here. In this case, the Hamiltonian we have extremely simple. Basically, we just have the kinetic energy contribution. Here, this is the total wave function of the system. We have n electrons here, so we have the position variables, the position vector, and the spin state corresponding to each electron. Actually, the Hamiltonian is spin independent, so the electronic states are going to be degenerate in spin. So we have spin up, spin down are going to be degenerated, and it's not going to be an important variable in the system. So here the Hamiltonian we have can be variables separated, can be separated in the variables of the electronic position vectors, and therefore we can apply the separation of variables method. And in this method we can express the complete wave function as a product of the wave function corresponding to each electrons. And our aim, therefore, is going to be to calculate which is the wave function corresponding to each electron. In other ways, this kind of model, the free electron gas model, is also called the independent electron approximation, because each electron acts like independently from the others. And we can do so, we can apply basically this kind of separation of method, this separation of variable method, whenever we are not considering electron-electron interaction. Of course, if we're including the electron-electron interaction, the separation of variable method cannot be applied, and the wave function, the wave function cannot be expressed in that way. So, as I've said, our aim is to consider to calculate which is the wave function corresponding to each electron. And for that, we have to plug the complete wave function here expressed in that way. And we have the wave function corresponding, or the equation corresponding to its electron state. And this is the equation that we have for its electron state. This is the one, actually. Of course, you can imagine this is the free electron, like Hamiltonian corresponding to its electrons. That, as we know, these are plane waves, the solutions are plane waves, and the label of these plane waves are the k wave vector, that of course is related with the momentum state of these electrons, which is h bar times k. This prefactor here is a normalizing prefactor, considering that the electrons are moving in a crystal of volume V, and the eigen value is k squared over 2. As we have said, the solid occupies a volume V, so that we consider some kind of boundary conditions on the surface of the solid. But we will not be interested in the kind of the properties of the electronic properties that the system will have on the surface. So we apply the simplest kind of boundary conditions we can consider, which are the von-Karman or periodic boundary conditions, which basically says that we'll consider the simplest volume for a crystal, which is going to be a cube. Of side, we'll consider the side of the cube is going to be L. And in these periodic von-Karman conditions, we'll consider that the wave function in one of the sides has to be the same as the wave functions on the other side of the cube. Of course, in case we were interested in the surface state, this kind of periodic von-Karman conditions cannot be applied. But we'll be just interested on the bulk properties. We are not interested, will not be interested here on surface states. So, applying this kind of von-Karman conditions, the wave function on both sides has to be the same. And in order to do so, this exponential here has to be equal to 1. So, or put another way, it means that kx, ky, kz has to take these values, which basically are integer times 2 pi over L. That means that the k wave factor is not going to be continuous, but we are defining a mesh in k space. And actually, the distance between these two neighboring k vectors is going to be really small, 2 pi over L. And considering the L is going to be very large, of crystal is going to be very large, this distance is going to be really small. And therefore, when doing the summations, it will be interesting to go from the summations, which actually are really in the k space, which are kind of, we'll need to make some kind of summation, but they are really tough to do summation. We're really interested in passing from the summation over k to integral over k space. And for that, it's interesting to know which are the number of k values, k states we have per unit volume in the k space. And this is this factor, this v over 8 pi over 3, which basically is the inverse of 2 pi over L to cube, is the number of k values we have if we consider a volume per unit volume in the k space. And this is the factor we need to consider when we are passing from a summation in k to an integration to the k space. So here we have solved and we know which are the wave functions corresponding to each electrons, which are plane waves. The k vector, considering this kind of periodic boundary conditions, are taking the discrete values, and is defining a k mesh here. And once we have the wave functions corresponding to each electron, we can build, therefore, the wave function corresponding to the complete n electron system. And for that, if we're interested on the ground state, we'll be occupying the k states that have been that we have defined for each electron state. So, and considering that that even though that here we are considering the simplest approximation for the wave function, which basically means that there is no antisymmetry here we are considering. We are not considering that the wave function needs to be antisymmetric, But we're going to apply the Pauli exclusion principle, which basically means that each k-state can be just doubly occupied. So having this k-state, we are going to fill the k-states we have defined with n electrons. So basically it means that n over 2 k-states are going to be filled with the electrons. And therefore, considering all the states that have been filled, we can calculate from here the total energy of the system with n electrons. That's going to be our next step.